I've always been fascinated by the Marvel technology and the superheroes, especially the materials they have available. Therefore, I just needed to make this episode with you. It is with Professor Aude Simar from Louvain University in Belgium. We will talk about a new alloy system. It's a self-healing alloy, so it is within the Marvel universe. And hopefully this alloy can be one of the future solutions in aerospace technology. So join in here and follow our conversation of the future alloys with self-healing effect. Hi, Aude.
Hello, Peter. How are you?
Fine. Welcome to the podcast Everyday Metallurgy. Today we'll have an episode on a new alloy. And first time I saw that written on LinkedIn, I was thinking vibranium, adamantium, and then Almazium. It must be the same family. It must be something from a futuristic movie with superheroes. But it is not. It is an alloy that exists in real life, and you are one of the developers of this alloy. Or can you give an introduction to yourself now?
So I'm Aude Simar. I'm professor at the University of Louvain in Belgium, so a little bit south of Brussels. And I work in the field of manufacturing for quite some time. I've done a lot of work on welding a long time ago, and then I moved to additive manufacturing. I guess this is a natural transition when you're talking about welding to move to additive manufacturing, because a lot of additive manufacturing processes are actually welding processes.
Yeah.
Were converted, and so that's how I changed my activities, but I still work on welding.
Yeah. But it's not regular welding, because you have started this work on Almazium. Can you disclose what Almazium is for an alloy?
So Almazium is an alloy made of aluminium, magnesium, and zirconium as main. Also, magnesium and zirconium are the main alloying elements, and the interest of that alloy is its self-healing capacity. So we usually talk about self-healing, even though it's not autonomous. So it's a healing capacity, but that only happens with a heat treatment, which is a little bit different to like say polymer-based self-healing materials that can exhibit a self-healing behavior at room temperature. That was disclosed by White in a Nature paper in 2001, which is quite some time ago now. So that gave a boost to the self-healing material field. However, at that time, it was really not easy to go towards metals, and that field. Metals were definitely not considered as a field for self-healing materials, but we've made a lot of progress in metallurgy, and so the field came in bits by bits to introduce in that. And so that gave me a chance in 2016 to start an ERC starting grant that allowed me to like explore this opportunity of developing all the expertise I had in aluminium alloys and develop it for self-healing materials. So that's how we developed the aluminium magnesium alloy, the proof of concept alloy that then got converted in the Almazium alloy, which is a high strength aluminium alloy that has self-healing capacities.
Yeah. And when I saw this, I thought, why self-healing? What can it be used for? My first thought was, well, aluminium alloys, they don't have a fatigue limit, so cracks will occur sometime if you are under high load for many cycles. But if you use a self-healing alloy, you must be able to heat treat these fatigue cracks and use the material as is again. Is that the purpose of it?
So it's an interesting comment because of course that's our aim. Fatigue is certainly something that is interesting when you, in particular when you talk about aluminium alloys because they're used for aerospace or space structures.
Yeah, exactly.
At this stage, one difficulty that is associated with healing cracks is the fact that cracks are open. Defects are porosities, and so the problem is that very quickly they get corrosion, and so making re-welding them is complicated. So at this stage, the alloy that we have developed, the Almazium, is an alloy that rather is able to heal damage at a scale of typically 1 to 2 micron. It works well. Up to 5 micron defects, it reasonably well works. Above that, we're really not fully healing. But what's I think interesting in that perspective is that of course we've thought about this question, and so now we're working with one of my PhD student, Mohamed Farag, is trying to develop something else in terms of healable materials at a larger scale, so at the scale of healing fatigue cracks.
Yeah, because I'm often met with people that comes to us and asking for steel alloys where it could have been smarter to use aluminium due to weight, but they cannot or they don't dare to go aluminium alloys because of the fear of fatigue. So it might be, I might lose business if you succeed.
Well, I think there is one issue that will not be solved as the price. We're talking about alloys that of course are expensive. So I think there's still a good future for steels for applications where we should be very careful on the price. Typically, applications where we can afford to spend a little bit more is typically space applications. They're definitely spending 1 kilogram in space is typically of the order of 10,000 euros. But in aerospace applications, even though things are changing, in the space it's also changing, let's say, but it's probably not it's remaining expensive to send material in space. And in space, we're in a situation where repair is very complicated. So if you have an overload at some point, what will you do except trying to weld in space? It's not really an easy thing to do. So I mean, if we can just locally heat and the material, or even imagine in like a future, imagine that there would be something in the alloy that could allow to electrically initiate heating that could favor this healing mechanism to be activated. Of course, that's not for tomorrow. That's our long-term goal, but that would be really great.
Yeah, I think to have an understanding on what you mean when you say heat treatment, we need to have some insight in the phase diagram, because for me, heat treatment is when we talk steel, it's 700, 900 degrees C, but where are we with this alloy?
So the aluminium magnesium phase diagram shows an eutectic at 450 degrees Celsius, and so this low melting point eutectic is something that we were actually trying to reach in terms of mechanism of healing. So the concept behind the healing was the fact that we try to reach this low melting point eutectic so we have local melting rather than global melting. At this stage, it depends a little bit on the magnesium content. In some cases, with a magnesium content of 8%, which is what we usually have nowadays in this alloy, that's what we use. We are more into the diffusion mechanism. We initiate a lot of diffusion that really goes to the open porosities, which are well, it's thermodynamically favored that you actually cause this diffusion towards the zones that are free open.
So,
That's commonly what causes precipitation also. Well, it's
yeah. Is it the eutectic condition? So is it the full aluminium, the 8% magnesium that melts and then what solidifies has the same chemical composition? Or will there be a gradient in the repair? Will it be higher in magnesium than the core material?
Well, Peter, are excellent questions because these are things we're trying to work out now.
Yeah.
So I would say that at this stage, it's possible to say that we've already identified that in partially healed, so porosities that are not fully healed, but that we've seen a reduction. We are capable of seeing some gradients in the magnesium content at the border. So that means that the magnesium contributes to this mechanism by its diffusion or its local melting of the second phase, this aluminium magnesium eutectic phase. Now, if you look at a porosity that is completely healed, usually we don't see any magnesium gradient or magnesium concentration gradient. And probably it's because the homogenization is very fast just after this mechanism happens.
Yeah.
So that's our belief, but it's something that we are still trying to work on.
So if we look at the heat treatment, typically heat treatment has a curve. So there's a slope up, there's a holding time, and there's a curve down. Can you disclose some of those figures?
Yeah, so what we did in the aluminium magnesium alloy that we already published is we got a 30 minutes at 540 degrees Celsius heat treatment. So it's about the eutectic, but that allows also to have a partial melting. What is said in the literature of self-healing materials is that if you have about 20% of liquid state, you will avoid losing the structural integrity, because that's really what we want to maintain. And so what we've been doing there is going to the synchrotron, the synchrotron in Grenoble, the ESRF, the European synchrotron facilities that allow us to observe by tomography some of the material before the healing and after the healing, and we really see a significant reduction in the porosity level. So just to clarify this, typically the voxel size is of the order of 35 nanometers when we use nano-holotomography. So this is a really new and incredible method that allows to really observe with a very high quality the microstructure and the evolution of the microstructure. And porosity is what is in situ, indeed. Yeah, so that's what we've been able to do. And recently, and that's the presentations we did at the AMS conference in September, where we actually showed that we do that in situ. In heating, but also in situ in tension. So we're doing in situ tension. We damage the material. Then we show the level of damage, and then we do the in situ heating, which allows us to like follow a particular defect and how it evolves with deformation, but also as it evolves with the healing process happening. In several cases, we've seen that actually it's not required to use the 30 minutes. Shorter times might be enough actually to have a mechanism of healing to appear. And probably this is related somehow to the level of the amount of liquid phase that we have. But it's quite difficult to identify what's the level of liquid phase we have. And it's also very dependent on the magnesium content, because as we discussed the phase diagram, if you have a higher magnesium content, you have a higher chances at this temperature to observe a liquid phase.
And then you have the zirconia in the material. What does that do? Does it change the liquidus point, or is it just a strengthening agent?
The zirconium is not there for the healing mechanism. That one is really initiated by the magnesium. So it's really magnesium that causes the healing mechanism, and that's why we started by using the aluminium magnesium alloy. And the zirconium is there for precipitation of Al3ZR precipitates, which are very high strengthening precipitate. And the advantage of these precipitates, and they've been used quite significantly in additive manufacturing, is the fact that these precipitates are very thermally stable, meaning that when we do the healing mechanism, we don't want the strength to drop down.
Yeah.
And so we managed to actually have a strength that is typically of the order of 350 to 400 megapascals of that alloy, while the alloy of aluminium magnesium was typically of the 150 megapascals kind of order. So that's what we've been able really to increase the strength of this alloy significantly.
Do they appear during the production, or is it a post-processing precipitation annealing you have to do to form these zirconium particles?
We believe that they appear during the solidification, but this is not something that we have been able to kind of observe already at this stage. Now we do this with additive manufacturing, doing in situ observation in additive manufacturing, considering the very fast cooling rates we're into. It's quite difficult, but I can tell you something. We tried in doing this alloy with casting, and that was a disaster. So definitely didn't get didn't get the really fine precipitates we are hoping to get.
Yeah, that was it. In fact, my next question. I could imagine the solidification of this would be dendrites. But you are doing this with laser powder bed fusion technique. Is there a reason, and how does it different look like?
Well, that was just telling about the fact that we tried it with casting, and that wasn't really a success. I think the very fast cooling rate is really interesting here because it favors actually the very fine precipitation and also the very fine distribution of the magnesium alloy. What we're seeing is usually that's the eutectic is a very fine cellular eutectic that really shows a fine distribution, a fine microstructure, and I think that allows for the magnesium to reach any damage region in a very fast manner, I would say.
Then I could imagine that if you heat treat a solidification structure from laser powder bed fusion, you have extremely small grains and not very, very small precipitation. But when you heat treat that at these 450 degree, or was it 540 heat treatment was that? It was high, yeah. Then do you see grain growth, or do the precipitation inhibit grain growth?
We do see grain growth, and that's one of the issues. But the really good news about zirconium, it's also a grain refiner, so it actually inhibits the grain growth also. Yeah. So that's really a good thing. But we do see grain growth. Very good comment indeed. We're actually observing that, and that is probably one of the reasons why we'll also have some modifications of the strength, but limited, hopefully limited. But we do have a little bit of softening due to the heat treatment. But the really good news is that it's quite limited, and also that we know that in aluminium alloys, what really causes the most strengthening is precipitation, and that one we are able to maintain.
Yeah. Then I would like to bring it to my own ball game, because I'm a powder metallurgist by heart, and laser powder bed fusion is also a powder metallurgy route. But do you see a potential in using some of the more old traditional powder metal routes like press center, MIM, hot isostatic press for an alloy system like this?
I guess it will be interesting to try. Well, we believe that the very fast cooling rates of the additive manufacturing contributes to this very fine microstructure. So we believe this is really needed, because we tried casting, as I told you, and that wasn't really highly successful. I mean, I would remain open to that question, because I think it's probably also going to help to have, let's say, a powder that is not melted then, and so maybe the fact that it's not melted will not favor the growth of really large zirconium precipitate, which was one of the issues we were facing in the casting.
In the casting, yeah. And this powder you are using, do you know how that is manufactured?
So the powder that we're using was manufactured in two ways. Initially, we started working with mixed powders. That was really our I mean, logically the first thing to do, because that's easy. You know, you just you buy a few powders and you put them together.
It's the easy way.
That was actually very successful for making our first alloy, and we managed to really do a lot of studies on that. So that's been working. But more recently, we went into considering to do a pre-alloyed powder. So we made it cast by and atomized and gas atomization by a company that made it for us. So the Almazium alloy is now actually a pre-alloyed powder that we've been able to manufacture.
Then my last issue, this is everyday metallurgy, and I would like to relate this to something in our everyday life. So when this alloy enters the market, where will we be able to see that? How will I be able to feel that in my everyday life?
Well, I hope longer term we can have that on cars and you know, a lot of I mean, probably it would be more reasonable to think that airplanes might be integrating this alloy. Your question about using other routes of manufacturing is certainly something we are working on, and that would contribute to allow it for a larger public, because one of the consequences of using laser powder bed fusion is the fact that it's usually smaller parts and with, let's say, a topologically optimized geometry, which is I mean, more commonly what you do with laser powder bed fusion. So it would be nice to be able to extend that to other alloys and to other applications and so on. But we're working on that. So other alloys is something we're considering, because aluminium magnesium is a common combination. So we could of course go much further than just classical laser powder bed fusion and only that alloy. That would be really interesting. And then the other thing is we could go for other types of applications, and that would require to change the manufacturing route. Probably powder metallurgy wouldn't even be the best way of going for that, but probably we should find other ways. And nowadays we are really considering to go towards other additive manufacturing methods that allow for larger sizes of parts, like wire arc additive manufacturing.
Like DAD.
Yeah, laser DAD and stuff like that. So these are techniques we're now considering. Also, additive friction stir deposition, which is one of my beloved old welding kind of technology that I've been very much working on. So these are things we're now considering, and probably that would favor to go to let's say more day-to-day applications but of course at this stage it needs to be validated more in the lab at different scales and show, for example, like the fatigue behavior, the impact behavior, and stuff like that, which are of course very important when we're talking about application of an alloy. Not to talk also about toughness, of course, that's very important. We at this stage we mostly our mechanical tests were mostly tensile tests, so that's too limited for going for applications and in fields typically like the aerospace field.
Yeah. This self-healing effect, you told it's known from polymers, but are there other metallic systems where the self-healing effect could be implemented?
There have been some nice work on the, for example, the iron gold system shows some healing capacities. There are quite some works, in particular in the Netherlands, that have been very active and more in the steel-based alloys.
Yeah.
The aluminum-based alloys. I believe that we're the only one working on that, but I hope this is going to make some babies, and that at some point we'll have a lot of people working on that. We've already shown, for example, in the 7075 alloy that by LPBF that we had some healing capacities as well. So we've shown it that at a lower scale, and the performances are not as good in terms of healing capacity, but also the magnesium content is lower. So I guess this is, well, we hope to be able to understand that and say that this is the reason for it, but it does show some healing capacities.
Yeah. So next step is to transfer this to other 3D print technologies like the DED. But where do we see more about it? You told about a conference. So where can I learn more about this new material?
Yeah, we have several publications that we've written on the self-healing capacity of the aluminium magnesium system. So that's definitely already available for the general public, and so in particular there is a paper in Materials and Design Journal that recently came out on the aluminium magnesium system, and so on the Almazium alloy. That's something that will happen very soon. So it's coming out soon, and I'd be happy to share that with your audience.
Wonderful. We can put it in the notes below the episode on YouTube, in the comments, so people can find them there.
Perfect.
Yeah. Oh, thank you very much. I have learned a lot today about a new field of me, because aluminium is not really my normal ball game, and self-healing is very new for me. So I am very thankful for your introduction to this new world for me.
Thank you so much. Very pertinent questions, and if the audience has any other questions, they'll be happy to answer them, and they can contact me, and I'd be happy to just brainstorm on this and hopefully bring in new people on this field that is very exciting.
I will encourage people, and if new questions appear, I will invite you for an episode 2 on this.
I look forward to that.
Thank you very much.
Thank you very much. Bye.